Hello everyone and welcome to CS224 Presentation 9. Congratulations! We are now moving from Chapter 2 into Chapter 3, wherein our topic will be machine level representations of programs. Okay, so what is a computer program? Well, we already know that programs consist of data and instructions. And in this class, we are trying to understand the relationship between the data and instructions in our programs and the systems that they're operating on. And so up until this point, we've focused a lot on the way that we can represent information as ones and zeros, and the way that those ones and zeros can be stored and manipulated within our computers. Now we're going to talk about the stuff that actually does the manipulating. Or as one student put it, instructions are the things to act, data are the things to be acted upon. So we've had a good introduction, a basic introduction to data and simple data types. Now we're going to look at instructions that can operate on those pieces of data. And we're going to kind of circle between these things. Okay, so we'll come back to more complex representations of data and so forth, and then we're going to circle back and look at the way our programs execute on the computers, and we're going to kind of bounce through these things throughout the term and build ourselves up on both topics as we go, because they're obviously closely coupled. So let's jump into a representation here then of a programmer's toolchain. So as programmers, you've all written source code, you've compiled it, you've executed it on your computers. It's important that we all remember that we are not actually writing the program that executes on our CPUs. Well, what on earth does the professor mean by that? Well, the program that executes on the CPU consists of a bunch of ones and zeros. And none of you have been writing all of those ones and zeros. And if you saw those ones and zeros, you would not recognize them as your program. So I think it's fair to say we're not actually writing the program that executes on our CPU. Rather, we use high-level languages to describe the program that we want to have executing on our CPU. And we utilize these things known as compilers or interpreters to then translate our description into an equivalent machine code representation of our program. Okay, so there are important processes involved in that compilation or interpretation, and so we're about to take our first peek under the hood and try to understand those processes and the relationship between the high-level code that we write and the machine code that actually executes on the CPU. In order to do that, it's healthy and probably necessary to understand a little bit more about what the compiler is actually doing. So again, there are different types of languages. Java, for instance, is known as an interpreted language. But no matter whether you're using a compiled language like C or C++, or an interpreted language, at some point, your high-level programming language has to map down to a set of machine code instructions. So the details may vary slightly between, for instance, what happens with a C program and what happens with a Java program. But the basics of what I'm about to talk about are going to have to happen at some point for any high-level program to actually execute on a CPU. Okay? So what we're discussing here is relevant in numerous contexts. All right. So we are using the GCC compiler in this class. And typically we just invoke GCC from the command line and we get an executable out. However, there's more going on under the hood than we've probably been aware of. The reality is that the GCC compiler is actually a set of tools that are being invoked in sequence for us without us needing to know about it most of the time. What are those tools? Well, the first tool is actually known as the compiler. Okay, so the GCC compiler translates our C program into a new representation or a different representation that is captured in something known as assembly language or assembly code. Now, assembly code is almost machine code. And what do I mean by almost? Well, there is a pretty direct mapping between each of our instructions in assembly code, or each of the assembly code instructions that were derived from our C program. Okay, so there's a fairly direct mapping between each of those assembly code instructions and a machine code instruction that can execute on the CPU. The difference is assembly code is not ones and zeros. It is a mapping from a bunch of ones and zeros to some kind of alphanumeric representation that's easier for us to understand. So instead of showing us, for instance, a set of ones and zeros that mean add, in assembly language we'll actually see something like the letters ADD to represent add. Okay, that's convenient. So assembly code is quote-unquote human readable. At least that's the case for a subset of humans who have worked with it enough that they can understand it. You are about to join that subset of humans. Welcome to the fold. Okay, so, but in order for assembly code to make sense, we need to know where it's going. Okay, so that assembly code can't execute directly on the machine. What happens in order for it to be able to do so? Well, it must be assembled. So the second step in the process of compilation is to take the assembly code that the compiler generated and to assemble it. And that's doing this mapping from each of those assembly code instructions into the ones and zeros that the CPU can understand. So can we take those ones and zeros and execute them? Not quite. Okay, close, but not quite. There will be, when the assembler is finished, certain pieces of information that are still missing. Part of the reason for that is that, for instance, in the GCC toolchain, typically source files are compiled one at a time. So if our program has numerous source files, then the compiler and assembler are going to be invoked numerous times. And so if you think about it, you probably have data objects and functions and things spread out in multiple files that are related to each other. One function calls another and passes data between them and so on and so forth. Okay, well, our programs ultimately have to live in memory, and memory is accessed using addresses. And so in order for our program to work correctly, then when we're calling those functions, the CPU needs to know where those functions live, for instance. That's not known to the compiler or the assembler. But that information can be learned or discovered, however you want to word this, by the linker. So the linker will take then all of the object code, it's known as, okay? If I didn't mention that, I'll mention it here. If I'm repeating myself, I apologize. But the assembly code that has been translated into machine code is known as object code. And so the linker will take all of that object code from all of those different files and tie those things together in memory. It'll lay everything out, and then it'll go, okay, so here's where the addition with saturation function lives, and it's called up here. So it'll fill in the addresses that are necessary in order for that to work. Okay, so the linker is literally linking together kind of those global things like functions so that our programs can execute properly. So when the linker is done, then what we will have is this executable set of binary, okay, that the CPU can read. Okay? All right, so we, at this point in our class, are going to start focusing basically right here. We're not going to spend much time looking at the linker yet. We'll get there, but for now we're going to be focusing on the stuff that's happening right here. The assembly code that our compiler can generate, the relationship between that assembly code and the programs that, the C-level programs that we're writing, okay, and then how that information is ultimately going to be executed on the CPU. Now, for this to make sense, we're going to have to dig a little bit deeper into the actual organization of our computers. So our programs consist of data and instructions, and these things are interacting with each other on and within these 5 high-level concepts that embody a computer. So our discussion about data has touched upon the topic of memory. Of course, we need somewhere to put the data, as well as the data path. We've talked about the way that operations which execute within the data path affect the bits that represent our data, and some of the nuances we need to be aware of. Okay, so for instance, our data path is doing modular arithmetic, not regular arithmetic, and so forth. So we've kind of touched on these two things. As we move into this idea of instructions then, we need to have a little bit more understanding of what's going on within the computer and what actually lives within the computer. Now, our instructions at some point are going to cause the control unit to exercise the data path and to interact with memory. Okay, now there's other stuff in this diagram, obviously the output and input, and we're utilizing these things, but we're kind of using them as black boxes right now. And we can kind of safely do that and work our way up. But for now, we're going to be focusing in the next few sections on the data path, the control unit, and the memory. And we're going to be doing this via these instructions, these assembly code instructions that we're going to begin to learn. Now, in order for this to make any sense, there is part of the machine that this diagram is currently abstracting away. Up until now, we have discussed memory as this kind of homogeneous entity that magically stores our data and gives it to us when we need it. Well, we're going to get rid of some of the magic and gain a better understanding of how memory is actually used within our CPUs. In order to do this, though, we need to discover a reality at this point, and that is that there are really two kinds of memory that our computer works with. Okay, so we're all familiar with the concept of main memory, and that's this, large resource where we can store things and read things by using an address. Okay, but there's another type of memory that's available to us within our CPUs, and that is known as register memory. What are registers? Well, like main memory, registers are locations where we can store information. However, there are significant differences between registers and main memory. So for one thing, as this diagram is trying to suggest, registers are small. Okay, they're kind of like little buckets where we can store a limited amount of information, and we'll have multiple buckets. But even with what would be considered a lot of registers, we're not going to have nearly the amount of storage space in our registers as we'll have in main memory. So relative to main memory, registers are small and there are very few of them. Okay, but there's another significant difference between registers that is in some ways the most important difference, and that is that registers are very, very fast when compared to main memory. Registers are built next to or arguably as part of the data path in the CPU, and they're built using different technologies than are usually used in main memory. And the result is that we can usually read from or write to a register in one clock cycle. Okay, that's as fast as we can do anything on the CPU typically is one clock cycle. Okay, whereas reading from and writing to main memory usually takes many, many clock cycles. So if we can, then we want to do operations on registers and keep the data that we're going to be operating on in registers as much as is possible. That's one of the ways we can optimize the performance of our programs. Okay, now some of you may be thinking to yourselves, well, wait, he's forgetting another type of memory. I'm not forgetting. We do have another type of memory in modern CPUs known as cache memory. And it arguably sits in between registers and main memory, both in function as well as in behavior, in that often we won't read information straight from memory to put it in registers, for instance. We'll read it from the cache. And if it's not in the cache, we'll get it from memory, put it in the cache, and then put it in registers. And often we won't write from the data path directly to main memory. We'll write to the cache, for instance, and then that will go out to main memory at some point in time. Okay, so cache certainly is an important part of the memory hierarchy. However, it's significantly different from registers and main memory in that the cache is not directly accessible to us via our instructions. Okay, the cache kind of operates in a way that is invisible to us in some sense. We can write programs, and those programs will execute without us ever writing an instruction that does anything directly to the cache. Okay, so does this mean that we don't need to know anything about the cache? Well, no. You'll recall earlier on in the semester, we talked about the relationship between the way that things are stored in memory and accessed and the performance of our program. Well, that is relevant to the cache as well, not just main memory, but also the cache. So we might be able to write programs that cause us just to waste an awful lot of time moving things around between main memory, the cache, and the registers. If we understand how the cache works, then we can optimize our programs so that there's as little of that going on as possible. We want to keep data that we need close by where we can get to it quickly. And so understanding things about how the cache operates can help us or allow us to indirectly manipulate the way that the cache behaves. All right, so we're not going to focus on that right now, and that's why the cache is not part of this diagram at this point in time. We're only going to focus on the two types of memory that we can access directly through our machine instructions, and for now that will be registers and memory. Okay? All right. Now, that's all I wanted to show in terms of diagrams. At this point in time, I wanted to jump over to a terminal window and actually demonstrate some of these GCC tools that I just talked about. So I've got a couple of simple programs I've written, one called Simple and one called Hello. Now, Simple is about as simple of a C program as you can write. It includes simply a pound include, which actually doesn't accomplish anything in this program, and I'll point out why in a moment, and one function that simply returns. And what we're accustomed to doing, so you can see here I have both of these C files, hello.c and simple.c. What we're accustomed to doing is invoking the compiler, GCC, and saying, all right, simple.c. We run it, and we get our executable. In this case, it's called a.out. And we can execute that simply by running it from the shell or from the terminal like this. Nothing appears to have happened. There was no useful input or output for this program. However, let's point out a few things. Notice the size of my simple.c file. It's 81 bytes. And notice the size of a.out. It's over 8 kilobytes. Okay, so obviously the compiler has done a lot of stuff between me typing GCC and it giving me this a.out. So let's break this down a little bit further. We can instruct the compiler to stop at various stages of the compilation process. For instance, I can tell it to stop after compiling the source code into assembly code, and we do that by using flags. So the -S flag will instruct GCC to stop after executing the compiler. Okay, so we do that, and what happens? Well, we now have a new file called simple.s. Now, I don't know why S is the flag that is used when we're trying to tell it to stop at the assembly language level. I try to remember it myself by thinking that, well, maybe someone couldn't say assembly very well, and they just called it assembly. Okay, it's terrible, I know. But it helps me remember. So the -S flag makes the compiler stop at assembly code, okay, or assembly language. And so that's what we have here. Now, this, as I said, is a human readable file. All right, so here I've catted the bytes, the information in that file to the screen, and you can see things that look human readable. You know, main, and then some words like move L, pop Q. Okay, so there's stuff that looks a little bit human here for us, and this is the stuff that we're going to be studying over the next couple of weeks. These instructions and what they mean. I'll point out right now that in this particular representation, this is an instruction, and this is one of its arguments, and it happens to be a register. So when we see this %sign and then some letters behind it, we're talking about a register. Okay? Now, there's a lot of other stuff going on here. I'm not going to jump into it at this point. I want to continue on with the discussion about these tools. So again, we started with this file, simple.c, and we have now compiled it into assembly code, and it's stored it in a file called simple.s. Now, let's take that file, simple.s, and let's run it through the assembler. So we can do that by saying GCC, and we want to tell GCC to stop after running the assembler. And so we do that with the flag -c. Okay, now I could feed as an input to the compiler at this point, I could feed it simple.c, or I could give it simple.s. I'm going to give it .s, but please understand I could just give it simple.c again, and it would simply run through the compiler and then run the assembler. But I can also say, hey, here's the assembly file. Go ahead and stop after running the assembler. And that's what we're going to do now. So what happens? Well, it has generated this new file, simple.o. And that contains the object code that resulted from the assembly code that we gave it. Now, notice a few things. Here's my .c file, and it's 81 bytes. Here's my .s, or assembly code file, it's 380. So you see kind of this expansion happening. And now, when I've gone to a .o file, notice we're over a kilobyte of information at this point. So this should tell us a lot about what we're doing when we write these high-level programs. Okay, you write a few pages, okay, a few thousand lines of code. That's translated into potentially hundreds of thousands of machine, or even millions of machine code instructions. Okay, so there's a lot of heavy lifting being done for us with these tools, and we're really lucky, we're really blessed to live in a time when they're available. Let's push this through the last step. So we've gone from a C source code file to an assembly code file to a object file. So we've gone through the compiler and then through the assembler. Now we need to go through the linker, and so if I say GCC and I feed it the simple.o file, we should get, well, I think I already had a.out sitting there, but let's now look at the timestamp on it, and you'll see that we've, let's see, did I or didn't I? Yeah, so you see the timestamp changed. Okay, so now this is a newly compiled a.out file, and again I can execute it and watch as nothing appears to happen. Okay, but it did. Now let's make this a little bit more exciting. Here's a simple hello world.program. Hello world.program, that's interesting. A hello world program. As before, I've included studio.h. I could have actually compiled that program without it because I didn't actually use anything that this library provided. But now I will. I'm going to use the printf function. And so I've really only added this one line of code to the simple.c program. But let's see how it behaves. So let's run the compiler again. And first I'll run the entire toolchain. So I'm going to compile hello.c. And now a.out is actually my hello program, and I run it and I get hello world. Okay? Now let's run through the other steps like we did before and just see if there's anything worth looking at. So I'm gonna open up here. Oh, I guess that's what I wanted. I'm gonna open up the simple.s file. Okay, so here's the assembly code for our simple.c program. Let's generate assembly code for our hello.c program. So we'll invoke GCC. We'll tell it we want to stop after the compiler. We want the assembly code, and we'll feed it hello.c. And now we have a hello.s file. Let's look at it and kind of compare and contrast it a little bit with the simple.s program. Okay, so here's hello.s and here's simple.s. And so you'll notice that there's similarities. We see a main in both of these. Okay, so something's going on here with these keywords with colons behind them. All right, but I wanted to show you in the hello program, you'll notice there's some other stuff that starts showing up. So here we have a string, and it's called that, the hello.world string. And so we can see remnants of the C code that we wrote showing up in this assembly code. All right, so it's not all voodoo. There are some hints here about what's going on. And as the semester progresses, this is going to become more and more clear to us what's actually happening and how our C code is being translated into this assembly code. All right, that's where I want to stop for now. In future presentations and homeworks, then we're going to break this down and actually study these instructions and gain a better understanding of how we can get the instructions that we want by changing maybe the way that we approach problems when we're writing C code. Not every C program that accomplishes the same high-level objectives does it as efficiently, and at some point that's going to have to do with differences in the instructions that are generated. And so we will use assembly code as our way of analyzing those instructions and better understanding our programs and the computers that they execute on. All right? Okay, well, until next time, I hope you have a good day.